morning all. My name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is image processing. Today I am discussing about smoothing and sharpening of the image. So what is smoothing and what is sharpening? How they are related, how they are helpful for the image processing. So color image smoothing is a part of processing or pre-processing technique intended for removing possible image penetration without losing image information. So analogically, sharpening is pre-processing technique that plays an important role for feature extraction in image processing. A method to sharpen digital color image that takes viewing a conditions and human vision models into consideration is described. Suppose I have one image is there. So as per human visibility, it is not possible to see the image, or it is typical to see the image. So I want to reduce the brightness of the image. I want to improve the brightness, or I want to reduce the color. I want to improve the color, whatever may be, as per our requirements. So smoothing and sharpening are unwanted color or unwanted edges. It will be sharpening and it will be smoothing. It is like one type of reducing the noises. So when we are going to the smoothing, a part of pre-processing technique. Okay, pre-processing means when we are getting the output, before the output only we are getting the pre-processing. So we are removing the possible image without losing any image information. Suppose I am giving the input image, I am getting the output image. But here, when I am applying the smoothing and sharpening, we will not any loss of information from the image. Just it is smoothing or sharpening, depends on our requirement. But we are not losing anything of the original image. So it will be not damage of anything. So analogically, sharpening is a pre-processing technique that plays an important role for feature extraction in image processing, and a method to sharpen digital color image that takes viewing conditions and human vision models into consideration is described. So this method combines a Laplacian or Gaussian transformation or operator with spatial filters that approximate the contrast sensitivity functions of human visual system. So what are the two important pre-processing techniques are there in the computer vision of the field or in the image? So it is our topic. Presently we are discussing about smoothing and sharpening in color image. Smoothing and sharpening in the grayscale also there, but our topic is discussing about especially for color image processing. So what are the two important processing techniques? That is smoothing and sharpening. But the method, it combines the Laplacian of Gaussian. So Laplacian or Gaussian operator, these are the operators are using for the transformation. So smoothing and sharpening is a transformation technique. We are transforming from one form to another form. Okay, that is a transformation or operator function with spatial filter that approximates the contrast sensitivity functions of human visual systems. So smoothing consists of the removal of possible image resulted from the image acquisition. So it consists of removal of possible image perturbations, means unnecessary or unwanted. Suppose one image is there. So I am taking one image. This image, some unwanted dots are there. So I want to remove like this. I am using smoothing. Sharpening means edges. When we are going for the edges, okay, sharpening I am using. So smoothing and sharpening are the very important role for color image processing. So smoothing and sharpening are the major roles, or the techniques, or the transformation, or the vector functions are helpful for the reducing the noise, removal of noise in the original image. So two important processing techniques with the computer vision field, that are smoothing. First one is a smoothing, second one is a sharpening. So smoothing consists of removal of possible image perturbations resulted from the image acquisition. What about the sharpening? in the change of improvement of the image visual appearance and the enhancement, the detail and borders of the image. There exist a lot of smoothing and sharpening methods that are able to improve the visual quality of the image. So main intention of the sharpening is a visual intensity, visual of the quality of the image. So we are not damaging anything, but we have to improve the visibility of the image. It is about completely from the human visual system. Okay, so smoothing and sharpening are the major things for the pre-processing technique for computer vision to removing the noise and sharpening of the image. Here I am taking one image. It is the original image that I am calling as a figure A, and it is a smoothing. Okay, it is the original image and it is a sharpening. You can observe here. Here, what is the original image and smoothing? What are the improvements are there? Here, the light focus is there. Here, the light focus. As per Huffman visual system, not able to see the image. So, as per the Huffman visual system, this brightness is very high. So, that is the reason we are not able to see as per human being system. So, when I am going for the smoothing, when this light focus is reduced, it is somewhat reduced. So, then what will happen now? It is somewhat visible, and you have to observe this dress and like this. When it is focus, the dress color is different. When I am reducing the focus, the dress color is normal. Okay, so as per human visual system, it is somewhat improvement is there. You can see here, it is a figure C and a figure D. So from C is the original image. So from the figure D sharpening process, it is a simulation in the MATLAB. It is completely about the MATLAB. So when I going for the sharpening, it is much clarity about this one. You have to see the dress. So here the dress is somewhat dull. Here somewhat brightness is there. So somewhat better from the original image. That is the sharpening of the image. So it is about the smoothing and sharpening from the original image. So smoothing is about the we are adjusting the brightness, and sharpening is that nothing but we are getting much clarity. We are getting much clarity about the image. So in the background, when some bricks are there, it is not looking like we are not identifying. But here, when I'm doing this one, what is the size of the bricks? What is the original size of the bricks? Also, we are identifying. That is the specialty of sharpening. So So, smoothing and sharpening, we are applying the MATLAB simulation to change the original image. So, however, the same does not happen with the simultaneous approaches due to the opposite nature of these two operations. So, we present a new model based on graph theory that allows us to improve the details of the image at the same time that the noise is removing. So, the color image smoothing is that the set of pre-processing technique intended of JK removing possible image attribution without losing any image information. So, when I'm using the smoothing, it does not happen with the simultaneous approaches due to the opposite nature of these operations, but a new model based on graph theory that allows us to improve the details of the image at the same time that the noise is removed. And the color image smoothing is the set of pre-processing technique intended for JK removing possible image perturbation without losing the image information. So what are the vector technique? What are the processing? What are the transformation techniques we are using? So that is we are discussing. Another one is a white Gaussian noise. Is the most common factor which can significantly affect visual quality of images. Each pixel of the image will be changed from its original value by some small amount that follows Gaussian distribution. So when I'm using the color image sharpening is a set of technique whose purpose is the improvement of the image, visual appearance and highlight or recover certain details of the image for conducting and suitable analysis of a human or a machine. But typical spatial filters for color image smoothing are based on the convolution of the image with the different corners depending on the intended result. So already we know that we can see here Laplacian of Gaussian, Laplacian of Gaussian operator or function, transformation function. So when I'm using white Gaussian transformation function, that noise is the most common factor which can significantly affect visual quality of the image. Each pixel of the image will be changed from its original value to the some small amount of that follows as a Gaussian distribution, white Gaussian distribution. But color image sharpening is the set of technique whose purpose is the improvement of the image visual appearance and highlight or recover certain details of the image for conducting a suitable analysis of a human or a machine. So it is a human visual system. So as per human visual system, we are applying the white Gaussian or Gaussian technique we are applying here. So spatial filters. So spatial filters for color image smoothing are based on the convolution of the image kernels depending on the intended results. When I using the spatial image, when I using the spatial smoothing, so spatial filters are using for smoothing. And what about the sharpening? So the color image sharpening is a set of technique whose purpose is the improvement of the image visual appearance and highlight or recover certain details of the image, conducting an suitable analysis by a human or a machine. But typical spatial filters for color image smoothing are based on the convolution with the different kernels depending on the intended result. So the color image sharpening is the set of technique whose purpose to improvement. So mostly spatial filters are using for the smoothing and the sharpening is for the transformation functions. Okay, so these are the very helpful for color image processing. For visual system. So smoothing and sharpening are the major roles for the reducing the noise or removing the noise in the color image processing as per the human visual system. But the pre-processing technique intended for removing possible image perturbations without losing of the image information. But analogically, sharpening is a pre-processing technique that plays an important role for feature extraction in image processing. But a method to sharpen the digital color image that takes viewing conditions and human vision models into consideration is described. So then we are combining the Laplacian Gaussian LOP or LOG operator with the spatial filters that approximates the contrast sensitivity functions of human visual system. So what are the two major important rule for pre-processing technique, that is a computer vision field, is a smoothing and sharpening. So when the smoothing is consist of the removal of possible image attributions as a result from the image acquisition, and the sharpening is a change or is a charge of improvement of the image visual appearance and the enhancement of detail and borders of the image. There exist a lot of smoothing and sharpening methods that are able to improve the visual quality of the image. So original image to the smoothing, original image into the sharpening. So the same does not happen with the simultaneous approaches due to opposite nature of these operations. We present a new model based on a graph theory that allows to improve the details of the image of the same time that the noise is removed. But the color image smoothing is a set of pre-processing technique intended for JK removing possible image attribution without losing of the image information. So when I'm using the Gaussian, so in the Gaussian, another is a major thing is a white Gaussian. So the Gaussian noise is the most common factor which can significantly affect visual quality of the image. Each pixel of the image will be changed from its original value by some small amount that follows a Gaussian distribution. So the color image sharpening is the set of techniques whose purpose is the improvement of the image visual appearance and highlight or recover certain details of the image for the conducting of suitable analysis of the human machine. But the spatial filter for color image smoothing is based on convolution of the image with the different kernels depending on the intended of the result. So it is about the smoothing and sharpening of the image. Another one is a color transformation. So when I'm using the RGB, the input function f of m comma n, applying the g of m comma n. So what is happening means histogram. So output equal to transformation function of input. Here what is the transformation function is a histogram. So it is the original image. It is a histogram image. Histogram means transformation function applied. So here I am applied the HSI, hue, saturation, and intensity. So when we are applied the hue, when we applied the intensity or saturation, applying the intensity HSI. So it is hue, the graph is like that. When I am going for the S, so it is not going for exactly 0, it is some 0.2 like this. So it is going like this. Here exactly 0, but it is somewhat curve is there, that is a intensity. The histogram before processing of the median 0.36, after the histogram it is at 0.5, is a somewhat improvement with that. So when the improvement is there with the help of histogram. So the histogram equalization is followed by saturation adjustment in the HSI space. So the fewest operations are involved in the HSI space. The computations involved in conversion back of the fourth from RGB space more than offsets of any savings in computations of HSI, hue, saturation, and intensity. But in the grayscale case, this transformation is useful to enhancing in detail of the embedded dark positions of a color image. But the complementation can be easily implemented in the RGB space. However, there is no simple equivalent of this HSI space of the approximation is possible. So when I am considering g of m comma n is equal to ka into f of m comma n. So g of m comma n is a output function and it is the input function and it is a transformation function. When I am taking the HSI, S1 equal to R1, S2 equal to R2 and S3 equal to K into R3. When I am going for the RGB, S1 equal to K into R1, S2 equal to K into R2, S3 equal to K into R3. When I am going for the CMY, S1 equal to K into R1 plus 1 minus K, S2 equal to K into R2 plus 1 minus K, and S3 equal to K into R plus 1 minus K3. So what are the color transformation techniques? The process of the components of the color image within the context of a single color model. So the formulation is similar to the gray level image transformation. G of x comma y equal to T into f of x comma y. That is the output is equal to transformation technique with input image. So f of x comma y is a color input image. G of x comma y is a transferred color output image. Pixel values are triples RGB, CMY, HSI or quarters CMYK. So SY equal to TI, SI equal to TI of R1 up to so on Rn. Here I equal to 1, 2, 3 so on N, and Ri is the color component of f of x comma y, that is the input, and Si equal to color component of g of x comma y, that is the output. So when I am taking the n equal to 3, that is R, G, B, n equal to 3. When I am going for the C, M, Y, K, so total 4, that is n equal to 4. So T equal to T1, T2, so on Tn, a set of n transformations or color mapping functions to perform R into Si. So it is a color image processing with cyan, magenta, yellow and black. How many are there? 4. So it is a n equal to 4, that is CMYK. So what is means? Input is a color image. It is a grayscale image with cyan, magenta, yellow and black. So CMYK. So these are the color components of this one. And another one is a RGB, red, green, blue, red, green and blue. So it is a color image, and output images are in the form of red image, green and blue. So it is the segmentations where I identify when it is red, when I am going to the green. So exactly the shape, the segment, and the top of the segment, another segment will be there. So when I am using the green, two segments are showing. One segment after the top, another segment is there. But here also there, but we are not identifying. Only one segment it is showing. But here in the one segment, another segment also showing. So here we are not identifying. Why? Because it is completely blue. So when applying the different colors, it is looking like a different segments. But identifying the segments are very important here. So when I'm going the HSI, hue, saturation and intensity, it is the original color image, that is a HSI, hue, saturation and intensity. So HSI color, so when it is color, it is nothing but a n equal to 3. So when I am using the HSI, S1 equal to R1, S2 equal to R3, R2 sorry, S3 equal to K into R3. When I am going for the RGB, SI equal to K into RI, I equal to 1, 2, 3. Why? Because 3 colors are there. So N equal to 3, I equal to 1, 2, 3. When I am using the CMY, that is N equal to 3, then I equal to 1, 2, 3. So we are decreasing the intensity value from figure A to figure B. But what is happening? Decreasing the intensity of the left image by the 30%. So we are using the 30%. 30% decrease in intensity. So we are decreasing the intensity values. So it is about the RGB, CMY and HS and I. So 4 different methods here applied. RGB, CMY, HS and I. So 4 techniques, 4 methods applied. So it is useful to think of a color image as a vector valued image where each pixel has associated with it as vector of 3 values. Each component of this vector corresponds to a different aspect of color depending on the color model being used. For example, if I am taking the RGB model, the 3 values of the vector respectively denote red, green and blue component of the color image. That HSI model, that the 3 values in the vector denote hue, saturation and intensity, that is a HSA. So RGB and HSI. So it is SI equal to TIA into R1, R2, R3. It is the output and it is the input and it is a transformation technique. So G of m comma n equal to K into F of m comma n. So when we are going for the basics of full color image processing, the full color image processing approaches fall into the two major categories. Approach 1, it is a approach 1 that process each component image individually and then form a composite processed color image from the individually processed components. And approach 2 is the work with color pixels directly in the form of color images. Color pixels really are vectors. For example, in the RGB system, each color pixel can be expressed as C of x comma y equal to CR of x comma y, CG of x comma y, CB of x comma y. So RGB, CR equal to red, green and blue. So we are applying the RGB. RGB. So for an image of size m into n, there are mn such vectors. C of x comma y is equal to x equal to 0, 1 to so 1 to so on n minus 1, y equal to 0, 1 to so on n minus 1. So the two approaches are there. Approach that process each component image individually and then form a composite process of the color image from the individually processed components. When I'm going for the approaches that work with color pixels directly in full color images. Color pixels really are vectors. But for example, in the RGB system, each color can be expressed as a this function. And when you are going for the gray level to the color, it is a spatial mask. I am applied here, spatial mask. When applying the spatial mask with f of x comma y, so f of x comma y is a spatial mask with intensity x comma y, that is a neighboring of the averaging pixel. But here, what is the formulation? The model of color transformation with g of x comma y equal to capital T of f of x comma y. The pixel values here are triplets or quarters. Analog to section gray level, we now consider SI equal to TI of R1, R2, R3, so on Rn, I equal to 1, 2, 3, so on N. So it is the model of color transformation. It is a transformation technique. It is a transformation vector G of x comma y equal to capital T of f of x comma y. These pixel values here are triplets or quarters, and analog to the section of gray level, we know that considering SI equal to TI of R1, R2, so on Rn, here I equal to 1 to so on N. So it is some examples of original color image. We are dividing it into the cyan, magenta, yellow, black and red, green, blue, hue, saturation and intensity. So it is about HSI, hue, saturation and red, green, blue, cyan, magenta, yellow, black. It is CMYK, it is RGB and it is the HSI. So the color image is converted converting to the CMYK, RGB and HSI. So any of this one, suppose I need a CMYK, I need a RGB, I need a HSI. You can convert any of this one. Depends on your application. Depends on your application. You have to choose all those things from the original image. That is a color image. So some operations are better suited to specific models, but the cost of converting between representations has to be considered as well. Example as follows. Suppose that we wish to modify the intensity of the image g of x comma y equal to k into f of x comma y. So output image equal to input with transformation technique. So HSA color equal to S1 equal to R1, S2 equal to R3, S3 equal to K into R3. RGB color space equal to SI into equal to K into RI, I equal to 1, 2, 3. CMY color space SI equal to K into RI, 1 minus K, I equal to 1, 2, 3. So although the HSA transformation involves the fewest number of operations, the computations required to convert an RGB to the CMYK. RGB or CMYK. Okay, any of this. How means when I'm using the HSI transformation, HSI to RGB or HSI to CMY. So the computations required to convert RGB to CMY image to the HSI technique to the offset advantage of the simpler transformation. So it is the RGB, CMY, HS and I. So suppose I'm taking the input image is a HSI, then output is converting to the RGB. So RGB is converting to the CMY or CMY is converting to the HS. If I have the HS, then it is converting to the intensity. So what are the two categories? First category is a process of each component image individually and form composite process the color image from the individually processed components. Second one is a work with color pixels directly. Color pixels really are vectors. So the second one is completely color pixels about color pixels really are vectors. So pixels with vectors. But here the process of each component which individually and form composite process of color image from the individually processed components. So the two major categories of the full color image processing approaches are pre-color component processing and vector based processing. Okay, it is the first one, per color component. Second one is a vector based processing. So per color component processing, each component each individually to form a composite process of the color image. Another is a vector based processing, the work with color processing as a vector directly. To make results of two approaches equivalent, the image processing method has to applicable to both vectors and scalars. The operation on each component of a vector must be independent of the other component. So this is about the basics of color image processing. So in the color image, what we discussed means majorly two types, two categories, two approaches. So first approach and second approach. So first approach is completely image individually and then form a composite process of the color image, individually process the components. And the second approach is work with color pixels directly to form a color image pixel with really vectors. Okay, when I'm using the vector function in the RGB, or each color pixel can be expressed in the form of RGB, in the form of HSI, in the form of CMYK. So it is an equation of C of x comma y equal to CR of x comma y, CG of x comma y, CB of x comma y with respect to the red, green and blue. So it is a grayscale image, it is a RGB scale. So RGB means so the figure A is a black and white and the figure B is the HSI model. So spatial mask of grayscale with RGB color images. So what is the formula is g of x comma y equal to capital T of f of x comma y. So here output function equal to f of x comma y is the input function with the transformation process. So the analog to the section of grayscale, we know that considering Si equal to Ti of R1 comma R2 so on Rn, I equal to 1 to so on n. So the full color image is converting to the cyan, magenta, yellow and black. That is the CMYK, and it is the first technique. It is the second technique. That is a red, green, blue RGB. It is the second, and one is the third one means hue, saturation and intensity HSI. So already you can see here there are different processes are there: RGB, CMY, HS and I. So those are the different techniques are there. So in the HSI, H is different and intensity are different. So these two models are the HSI. That is H, S and I. So HISC is one graph and the I is another graph. So that is a transformation of process. So first method about cyan, magenta, yellow and black CMYK. Second one is a red, green and blue RGB. Third one is a hue, saturation and intensity HSI. But some operations are better suited to specific models, but the cost of converting between representations has to be considered as well. But I am taking one example: g of x comma y equal to k into f of x comma y. That means output image is nothing but a input image. But what is happening means here I am applying the transformation technique. Here transformation technique is nothing but a with vector functions. So HSI color is when I'm going to the HSI, then what are the conditions means S1 equal to R1, S2 equal to R2, S3 equal to K into R3. But when I'm going for the RGB color, Si equal to K into Ri, I equal to 1 to 3. When I'm going to the CMY color, Si equal to K into Ri of 1 minus K, I equal to 1 to 3. So when I'm going to the HSI transformation, so what is the need means if I want to convert the HSI to the RGB or CMYK, what is the process? What are the processing is there? So when I'm going for the RGB and it is the CMYK. So what is input means HSI. So HSI to RGB, majorly red, green, blue. But when we are comparing the figure A and the figure B, somewhat they are different. Why? Because here CMYK, the different colors are there, but RGBs are different colors are there. So depends on your segmentation or your identification of the image, you have to convert to the HSI, RGB and CMYK. It is a graphical information about RGB, CMY, HS and I. And what are the major two categories are there means process each component image individually and form composite process color image from the individual processed components. So the work with color pixel directly, color pixels are really are vectors. So what are the two major categories of full color image means peer color component, vector based processing. So peer color component processing is nothing but the process of each component image individually to form a composite process of color image. Vector based processing is nothing but work with color pixels as a vector directly. But to make results of two approaches, the image processing method has to be applicable to both vectors and scalars. So vectors and scalars. So vectors means transformation technique. So the operation of each component of vector must be independent of the other component. So when I am using the vector, it is the independent. So it is about the basics of full color image processing. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.